Okay, if you just joined, good morning. I appreciate if you turn on your camera. Again, I have to mention that all the time. So last week we talked about the correlation coefficient, or R. Today we're going to review it a little bit, then we're going to talk a little bit more about the regression. Correlation, if you remember, we mentioned like one of the important things, you don't want to confuse this correlation coefficient or R with the causality. We said two values can have relation, or for example, in this case, linear relations without basically causality. I mean, they might be related, but it doesn't mean that necessarily they cause each other. And if you remember, we show you this figure that if R, let me go and see what we have. So basically R is measuring linear association, and I mentioned it, and again, I want to highlight that it just mentioned linear association. Two values might be related to each other, but not in a linearly, so R is not a good measure for that type of relations. So it's based on a standard unit, so it's unitless. It's like a standard unit. When we were talking about a standard unit, we mentioned that it's unitless. So R is also unitless. It doesn't have any unit. It always comes between -1 all the way to 1. R1 is basically, it means a scatter, or that the data are perfect. Basically, there is a perfect correlations between the data, or your scatter plot would look like linear, like this, by sloping up. If R is -1, it's going to have a slope down, and it means, again, negative relationship, but still have a relationship. R0, something like this. If your scatter plot look like this, basically there is no linear relationship between these two values that you are measuring. So just a short, basically, revision on that. We mentioned how to calculate. It's basically average of product of x in a standard unit, basically in y in a standard unit. If you remember, that was how we were calculating, and because we are calculating it based on the standard unit, so R also has no value. So we call it correlation coefficient for R. We may refer it both ways, and it measures how clustered the scatter is around this basically a straight line, or basically you can see how a linear equation can describe your data. You can see it like that way too. So let's talk about some properties of correlations, or properties of R. It's pure number with no unit. R is not affected by changing unit of measurement. We mentioned this. We're going to see some example of this. How it's if we change the unit of measurement. I think we had one example last week. We changed the unit, but the relationship between numbers still stays the same, so R value doesn't change. It's not affected by switching the horizontal and vertical axis. So let's see these properties in real data. So let's call, again, the same table, the SUV tables. You remember this table called hybrid that had all the hybrid cars up to, I don't know, 2007 maybe? With their vehicle, what is the model, the year, the price, acceleration, mile per gallon, and what is the class. So here we separate SUV class from that data to just look at this SUV table. Is it clear? You can see properly my screen? Because I noticed some people see it's the cut version of my screen because it's wide screen. So if there is any problem, let me know so I can adjust the size. So we have here a SUV table, all the SUV hybrid cars. Let's do the scatter plot and see what we see. So this is the same figure we saw last week also. So what do you think? Is there any relationship? What would be the R value if you can just say based on the scatter plot?
Around 0.4.
0.4.
Yeah, because you can see a pattern of a diagonal.
Okay, so you
But
see,
they're very, very, very scattered.
Umberto, you want to add something?
Yeah, to maybe like 0.5, 0.6. I
0.5.
don't know. I don't know how much the ones that are really far affect.
Yeah. So I mean, just what you were saying, the number you're saying, of course, it's very rough estimate, but how you're looking at it is like you considering it's a little bit like upward. If you don't consider this outliers, it's upward. So you consider R value is going to be positive. Then you say they are going to affect, so it's not going to be that high. So we're going to see that. So here I'm basically defining this function that we saw before, basically standard units that convert any array of numbers to standard unit, standardized, that returns basically convert all my tables into a standard unit. And another function, correlations, that calculate basically the correlation or R value for my two numbers. So you can see here, you get the standard unit of X, the standard unit of Y, multiply them, then you get the mean of it, average of it. So that's basically how you calculate R. So let's see, the correlation is 0.48. So you are both equally close to this. As I mentioned, okay, now we want to check those properties that I mentioned. For example, R is pure number with no unit, and it doesn't affect changing the measurement. So here, what I'm going to do, I want to convert this price this is like 36,000. I want to divide it by 1,000, so just to have 36.6. So I convert the value in my price, as you can see here, I divide it by 1,000, and I scatter plot it. So you can see the number here is in 1,000, for example, 20,000 to 100,000. So I change this value. So I want to calculate again the correlation and see if the value change or not. So as you can see again, you get the same value exactly. So R doesn't change by changing the unit of basically measurement value. And if I switch the acceleration and the price, okay, again, I'm going to expect to see the same R value. So this is just to show you this property that we were talking. It's not affected by changing unit of measurement. It's not affected by switching the horizontal and vertical axis. So let's talk about interpreting R and what you need to take care of it. So as I mentioned again, even, for example, the perfect correlations, if you have R1, it doesn't mean this, for example, X causing Y or Y causing X. So causality, you cannot conclude from R any type of causality. You can just conclude relationship, linear, and just linear relationship, not any type of relationship. So you have to watch for non-linearity. That's why we mentioned you better first basically draw your figure, draw basically, for example, scatter plot, then see how is it, then, for example, go for calculating R or maybe not R. So watch for those nonlinear relationship between two values. So basically, you better visualize first, then see it. So R affects by outliers. So you have to watch for outliers. It's not necessary you can ignore the outliers, but you know already the outliers affect your data a lot. So you have to watch for those. And last one is ecological correlations based on aggregated or average data. So I'm going to talk about this with example because that's make it more clear. Basically, ecological correlation is correlation between two variables that are grouped by the mean, not just for the individual, but for the group. So that becomes a little bit confusing or misleading. I'm going to show you in the code. So visualize, then quantify. Let's consider this scatter plot for my data. Okay, I have two x value, y value, and this is my scatter plot. So what do you think the correlation going to be for this scatter plot? Any guess, rough estimation? My R value.
0.
0.
Yeah, I think.
So it's 0, exactly. So, I mean, just looking at it, you can see how I draw this line. Basically, it's x to the power of 2, okay? There is obvious relationship between x and y, but it's not linear relationship. That's why our value becomes 0. So that's why you have to basically visualize first, then quantify, because for this type of graph doesn't make sense. I calculate R value. But so just looking at this, I calculate R value and I say, okay, there is no relationship between these two numbers, which is absolutely wrong. You can see there is obvious exponential relationship between x and y value. So let's look at this set of table. So what would be the R value for this scatter plot? X, Y.
1.
Yeah, you can see there is a direct relationship, right? Exact. So R value is 1, but for now I have the same lines and I have one single outliers here. So any estimation? You think how much this single point will affect my R?
0.8.
0.8?
0.5 maybe. I don't know.
0.5. Okay, 0.8, 0.5. Let's see. R value is 0. So you can see this single particular outliers data can totally change my relationship from perfect relationship to perfect linear relationship to no relationship at all. Because in this particular example, because I have just 4 data point, then 1 outliers, which is too much, basically too far from my points. That's why you see R. But always outliers will affect your data. So let's look at this table. So you have this table that we have 4x value, 4y value. So I want to see the relationship between x1, y1, x2, y2, x3, y3, and x4, y4. So I run these functions, it doesn't matter really, it's just to print some numbers and to compare these values together. So for x1, y1, you can see the mean are 9, for y1 mean is this, standard deviation are this, and R value is this, right? So for x2, y2, for this column with this column, x2 column with y2 column, you can see the same mean standard deviation R is the same for all of them, x3, y3, and x4, y4. So I get same mean standard deviation and R for all these, comparing x1 to y1, x2 to y2, 3 to 3, y3, x4 to y4. You can see, if you just see these numbers, you may say all the data are same, or if you maybe visualize them, you're going to see the same scatter plot, because mean, the standard deviation, and R is the same. So now let's have them the scatter plot. So this is for x1, y1. As you can see here, this is for x2, y2. This is for x3, y3. And this is for x4, y4. So you can see all these 4 different scatter plot are resulting in the same R, same standard deviation, same mean for x and y, but they are totally completely different. So that's why, if you go back to what I said here, is like visualize, then quantify. It's very important to visualize first to see how your data look like, and then quantify basically do the measurement. So about that ecological correlations that I mentioned, ecological correlation, let's look at, I'm sorry. Let's look at this table. This is a table considering United States different states with their grade in SAT exam, the exam that they require to basically get admitted into university. So you can say you have all the states with their participation rate and the grade, average grade for critical thinking, math, writing, and combined. So if I order this by math to see which states are doing better in math, I get this data. So we can see North Dakota, Illinois, Iowa, Michigan, they are the top 4. Minnesota, they are top 5, let's say, in math, okay? I'm ordering by the math. So if I look at critical reading, so I get again North Dakota, Iowa, now South Dakota came up, Illinois, Minnesota, but it's still 4 out of 5 states are the same. So maybe I can say there is a relationship between math and critical reading. If you are good at math, then you would be good at critical reading, because what I see, they did the same, okay? The top states are almost the same in the math and in the critical reading. So in order to see if there is any correlation, so I can basically scatter plot that. I'm scatter plotting this data, taking critical reading and math, okay? So what I see, it's pretty upward close line with high, very, very high correlations, right? You can see the correlation is 0.98. So I have this question for you now. Can you from this conclude if for individual, if you are good at math, it means you are good at critical reading?
Yes.
Any other idea? So remember, this table is for average in all North Dakota state, all Illinois state. 4.6% of the students attend this exam, and this is the average of all the students in this state. So I did this correlation. I did the scatter plot. I calculate the R value, and I see pretty high correlations. So the question is, based on this, can you conclude for individual, if you are good at math, you are good at critical reading? So Umberto said yes. Everyone thinks yes, or anyone has different idea? Okay, I don't hear any idea, but you have to be careful with this type of data that are average, or for example, the mean of a certain group of people. Here, you cannot conclude from these particular correlations. You cannot extend this group correlation to individual correlations, okay? Because this data is not coming from individual people. This is coming from average of people, average of a lot of students. And then again, you see their participation rate is different for different states. For example, here, only 2.3% of the students are taking the SAT exam. So we cannot extend this for saying for individual students, if you're good at math, you are good at critical reading. That might be a case, but we just can't conclude from this particular data or these particular correlations. Because it might be one student doing awful, okay, in math, great in critical thinking, another student doing awful in critical thinking, great at math. When you average them, you're gonna get different, basically totally different numbers. So that can't be extended to individual students. So those are basically the last point I mentioned, those ecological correlations that are based on aggregated or average data for a group of people. So you have to just be careful about this type of data. and other type of situation for interpreting the R. Let me see. Okay, any questions so far? Okay, so let's talk about linear regression. So the linear regression is basically to model the relationship between two variables by fitting a linear equation for example, x and y. So you want to see if a linear equation can describe your data. Okay. So let's go back to the code and let's look at the table that we saw in the second or third weeks, the Galton table. We said we mentioned Galton was a scientist living in the same era with who was the other one? You remember? I forgot the other one. I said they were family. They were cousin. So anyway, it's a scientist living like maybe 2 centuries ago. So the table was showing us the mid-parent average height of parents and the child height. So you had a basically average height of parents and child. So basically the table is showing this, Galton was trying to see if he can predict the height of the child based on the average height of the parents. So he started surveying different families, got the data, sorry, and get this table. So this is the same thing we saw before in second week, if I'm not mistaken. So let's first do the scatter plot of the data and see what we see. So you can say there is a little bit upward relationship between data, but data is very much cloudy. So R value shouldn't be that high, but still, if there is, it's not 0, it should be positive, right? Maybe 2.2, 0.3. So if you remember what we did last time, we calculated this, basically, we limit our data to this, for example, for this 2 point, I said, I want to look at all this data from 67.5 to 68.5 in my mid-parents, and I'm going to average all those basically data, and I'm going to, based on those average, I'm going to predict the child height. So basically, I'm sorry, I'm gathering all those data and I'm calculating this particular point or average all those points falling between these two data. So we did that. So basically, this is the all these data points that are between 67.5, 68.5 for my mid-parents. I get the child, and if I get the mean, so this is 66.2. So that's the yellow dot is that dot, 66.2 average of all those mid-parents for my child. So we did the same thing last time. Okay, so we tried to predict using this. This was the first prediction example we saw, and it was like maybe second week. So I'm going to define this table, which returns basically a prediction of the height of the child whose parents have a mid-parent height of parents. Okay, so I'm defining this these functions that does exactly the same thing. I give the same range in my data, and it calculates the mean of that to predict the child or the child's height. So for example, for the mid-parents around 68, 0.5 up, 0.5 down for 68, I get this estimation for my child's height, 66. For example, for 74, I get the estimation is like I estimate if my average height of the parents is around 74, I estimate the child would be somewhere around 70 inches tall. So if we do that, so what I'm doing, I'm just calculating it for all the values to have the, let me show you before this. So what I did here, I have this table, I appended these predictions for all the points in my mid-parents. If mid-parent is this, I predict my child would be 70, for this 70, 70, for, you can see for different mid-parents, I'm basically measuring different predictions. So if I scatter plot this, you see this yellow line which is my prediction for all this line of the data. Is that clear what I'm doing here? Any questions? So what I did here, basically getting all those dots in, for example, around 65, getting average and considering that the prediction for the child height. So you can see we come up with this scatter plot, which is the yellow one is the child predictions, the height of. So you can see this is like a linear line passing through all my lines that I had. So you might wonder, is that any relationship between this and linear regression or the R that we were calculating? So we're going to look at that. So what we did here, we use a visualization for X and Y pairs. We group each X with a representative X value. We get the average, the corresponding Y value for each group. These are the things I did in that piece of code. So we get 1 point per representative X value and average Y value. And then we saw if the association between X and Y is linear, then the points in the graph of average tends to fall on the regression line. So that basically this yellow dots, which are my prediction by averaging all those data, is tend to fall in my regression line. I'm going to draw that later. So let's talk about regression to mean. It's basically a statement about X and Y pair measure in a standard unit. This basically describe the deviation of X from the 0, deviation of the Y from the 0. And you can basically get this equation. Your Y in a standard unit is equal to your R value multiple your X and a standard unit. So R is your correlations, Y is your regression line. So this is not true for all the points, but it's a statement about the average. But considering this equation, you know R is between -1 and 1, right? That's the thing we already talked about. So considering R is between -1 and 1, you can say on average, Y deviate from 0 less than X deviate from 0. It's obvious conclusion from these equations. This is the equation for regression line. You have your Y in the standard unit is equal to your R, which is the correlations, multiple your X in the standard unit. And Y always deviate less from 0 because R can be, for example, 0.8, whatever between -1 and 1 is going to deviate less, Y going to deviate less comparing to X. It's just a normal conclusion from this. So from this point, you remember this is the standard unit, okay? And this is also a standard unit. So if you remember how we were calculating a standard unit, it's like you get, for example, Y in a standard unit, you get Y in normal unit, you diffract from average of Y, then you divide it by a standard deviation of the Y. That's how we were calculating the standard unit, if you remember. So if you want to convert from a standard unit back to the normal unit, now you go basically do some manipulation here. You get your Y in normal unit equal to your Y in a standard unit multiple your standard deviation plus the average. This is normal, basically, how to say? If you manipulate this equation, you get this. So this is just for you to remind you how we were calculating a standard unit. We had the normal unit minus the average of all the data divided by a standard deviation. That would be your standard unit. And you can go back to your standard unit from your to normal unit from your standard unit if you have a standard deviation and average. Let's look at this in a data. So this is the same data, child meet parent from the Galton table. So this red line is just a regression line that I think maybe that can represent my predictions. Okay. So I draw this. Sorry for the noise. Can you hear me clear? Or okay. So the red line is basically I just draw a random line that goes through all my points, and I think okay, this red line can maybe predict my data. This green line is the line that I want to predict my child height in this particular point. Remember, just remember, I converted them in the standard unit. Okay, my mid parent and child now is converted to standard unit here because I call this standardized function that I called it before. I used it before. But if you get this intersection between red line and green line, you remember this was my prediction, right? My prediction was falling somewhere in the middle of these lines, but here it's falling here. So you can say the red line is not a good line to represent or to predict my data. So in this figure, I draw this blue line, which is exactly my regression line. That's why I call it with R. Here you can see the R. So that's basically my regression line going through all these points. And the intersection between the blue line and the green line is falling here. It's look like exactly it's falling the same point that my prediction using the average is falling. So using average, I get this point for my prediction. Now using regression line, I'm getting this point. So you can say it's more or less falling the same. So we're getting basically the same conclusion from calculating the average or calculating the R, then drawing my basically regression line and seeing the intersection with my data. So remember I told you if you switch the mid-parent child, if you switch the X and Y value, you're going to see the same value. So if here I'm switching child and mid-parent comparing to this, then I draw my regression line. It's still the same regression line, so it doesn't change switching these two values. Really sorry for that, it's super annoying. So here I'm calculating my mean for my parents, standard deviation for my parents' data, and also I do the same for child, mean of all the child value, standard deviation, and this is R value. Okay, so here I'm just calculating these values for my table, mean, standard deviation for parents and child. So using these functions, now I can predict the height of my child with using R, not using average anymore. So the equation, if you remember, the standard unit for my parents is the average, the normal unit minus the mean divided by the standard deviation. And for the child is the same. For child, okay, I'm using now R multiple parent standard unit. So you remember the equation. So the equation tells you for Y. For example, here in this on that particular case, my X is my parent's standard unit. R is that correlations of the data, and I want to calculate my child. Okay, using this equation. So I calculate parent standard unit, then I have my R already calculated here. So R multiple parent standard unit is child standard unit. And my function returning the normal unit for child. And to convert the standard unit for normal unit, you do the standard unit multiple standard deviation for child plus child mean. So just don't get confused what's happening here. I'm predicting my child using the R value, using the R value, and then I return the normal unit using this equation. So for 68, I predict this. For 74, I predict this. So if you remember this two line, 65 here for 68, 69.8 for 74. If I go up, what we did here, you get this using the mean, using the average of data. So you can see it's pretty much close to this. There, using R, you get 65 for here, you get 69.8 for this one. So you can see we're getting pretty close data using our R value as well. So if I scatter this data, so this is my data earlier, okay? This is the exactly same figure here that we calculated with my all the dots, yellow dots that I calculated using the average. And here I have the same figure. I draw this blue line, which is my basically predictions using my R value, or this one, okay? So you can see it's following the same points that I had. Some of them a little bit far away, some of them exactly the same, but it's following the same patterns. Using R, okay, using my regression line basically, and using that averaging all the values and then calculating my predictions. So we got the same point. Is there any questions so far about what I did? Okay. So if everything is clear, I have these questions for you. I have a course that has a midterm of average 70, a standard deviation 10, and a really hard final exam that my students end up to having average of 50 with a standard deviation of 12. So if the scatter diagram comparing midterm and final scores for students has a typical oval shape with correlation of 0.75, then what do you expect the average final score would be for students who scored 90 on the midterm? And another one, what if the students scored 60 on the midterm? So can you please take a piece of paper or just calculate it in your head? So the student's getting 90 in the midterm, so you want to predict what would be his final exam, final grade for final exam. So I give you like 2 minutes. I mute this. So.
The standard unit conversion was the value minus the average over the standard deviation, right?
And you remember this was our equation based on the standard unit, okay? Y in a standard unit, R multiple X in standard unit. So basically you want to, here you want to, based on the midterm grade, you want to calculate final grade. This equation is a standard unit, but here, this is the way to convert them. And this is the question.
I believe the one that scored 90 would have an average of 68 on the final.
Can you talk a little bit louder? I can't really hear for this.
Oh, sorry. I believe that the student who got an 90 on the midterm is expecting a 68 on the final.
Okay, so can you tell us how you calculate that?
So I grabbed the 90 and I transformed it to the 90 on the midterm. I changed it to standard units by subtracting 70 and dividing that result over 10. That gave me the standard units of X. That was multiplied by the correlation of 0.75. And then I transformed it back to normal units for Y using the average of 50 and the standard deviation of 12, which is, I believe it was 1.5 times 12, and then plus 50. Then I got the 68.
That's correct. Anyone calculated for the 60?
Sorry, can you repeat?
I mean, anyone calculated for these students?
Oh, not yet.
This is 68 for the first one, as David Garcia said. For this one,
I think it's 41.
41.
Yes.
Yeah, correct, I think. Okay, I just repeat what David said, just if you didn't catch it correctly. So here, what you can do, you can go two ways. Basically, you can calculate using your normal unit or standard unit, which is much easier using a standard unit. So your student get 90 on the midterm. In order to convert this into the standard unit, you can say 90 minus average, which is 20, divided by a standard deviation, which is 10, so you get 2. So your X value here is in a standard unit is 2. Your R is 0.75. So if you say 2 multiple, maybe I can draw maybe. Your X in a standard unit is 2. So now you say 2 multiple your correlations, you get 1.5. Then what it means, your Y value is 1.5 above your, because Y is now you get Y in a standard unit equal to 1. Sorry, that's awful. Equal to 1.5. Okay, so that what it means. That means like your Y value is 1.5 above your basically a standard above your average, right? So you get 1.5. And you have your basically you have 1.5, you have this 12. If you can multiply this, you get 18. 18 basically grade above your 50, you get 68. So you can do the same for 60. Calculate, convert it to the standard unit, because it's much easier if you go using that equation for a standard unit. If you convert to use this one, it make your life much easier. You convert the value into the standard unit, you get the Y value in a standard unit. Then if the basic question is asking you to give it in the normal value, for example, in the grade, so you convert your standard unit to the grade. That makes it much easier. So let me show that in the in here. So basically, I put the same data here for the average for X for my X standard deviation. For Y, my final one, the standard deviation for the final, and the correlations. So if I calculated this, it's basically I don't know how can I make it much more clear than this. So you get 68 for the first one, 41 for the second one. So as I mentioned, you get this is converting the value to the standard unit. Now you have a standard unit, you multiple R. Now you have that Y value basically just using this part. Now you want to convert this Y value in a standard unit to the normal unit. So what you do, this part is your Y in the standard unit. You multiply standard deviation and add the average, you get your final Y value. So any questions? Any doubt? No? Okay, so let's continue then. So let's talk about slope and intercept. So this, the same equation that you remember, Y in a standard unit equal to R multiple X in a standard unit. But it's the same thing. I just put that equation in normal unit. So if I put those in normal unit, you get this equation. Don't just let it confuse you. It's the same thing. Y in a standard unit equal to R in X in a standard unit. So this is Y, this is X, this is your R. So you can do that in this way too. Like if your Y in normal unit equal to a slope multiple X plus intercept. So your slope of the regression is basically R divided by standard deviation of Y over standard deviation of X. And your intercept would be average of Y minus a slope multiple average of X. Average of Y minus slope average of X. This is your intercept. So this is, maybe it look confusing a little bit, but if you just do some algebraic manipulation using this, you get these values, okay? So don't let it confuse you. It's the same thing. It's the same with X in a standard unit, Y in a standard unit equal to R multiple X in a standard unit. I put them in the normal unit. Then I do some algebraic manipulation. I get these equations. So this is basically, if you pay attention, this is your linear equations, okay? This is like I say, for example, Y equal to 2x plus 3. This is my linear equation, okay? So this is the same thing we are doing here. This is basically your slope. This 2 would be your slope, and 3 will be your intercept. Is that clear? It's just some algebraic manipulation, nothing happening here. I just wanted to include this because we're going to see some. So I defined here the same functions for a slope to calculate the slope using the same equation. To calculate the intercept using the same equation. Okay, this is the same thing that we saw in the slide. So I'm calculating this, R multiple standard deviation of Y divided by standard deviation of X. It gives me my slope. Then average of Y mean minus my slope, multiple my mean in X, it's giving me my intercept. So let me run this. Let's look at that table that we looked the first week in our class. If you remember, we look at this novel, Little Woman. And then if you remember, we were seeing some graph. We scatter plot this, if you remember, the relationship between the number of periods and number of characters. This is the same thing we did in the first class. So this is number of periods in each chapter. This is the number of character in each chapter. So we draw this scatter plot to see if there is any relationship between number of characters and number of periods. Do you remember that this one? So what you can say, what you can see here, You can see it's falling pretty much in the same line. There is look like has a strong correlations between number of periods and number of characters. So it means the more periods you have, the more characters you're going to have. Or the period can basically represent your sentence. The more sentence you have, the more characters you're going to have. So if I calculate the R value, you can see R is 0.92, which is pretty high. There is very high correlation between number of characters and periods. So I defined this function feed, which is return the height of the regression line at each x value. So I'm having this now. I want to draw basically a regression line here. So okay, let me show you before this one. So what I did here, I have this table. So using the equations that I showed you earlier, okay, the slope, intercept, okay, so I calculated my values. Let me go back to the equations. So I'm using this equation now. I'm using these equations. I want to know my y in normal unit, okay, using my x in normal unit, but calculating using a slope and intercept. Okay, that's what I'm calculating in that function using these equations. Exactly as you can see here, it's the same equation. I have my slope, I have my intercept, then I calculate that value. This is my x value here. This is my slope, my intercept. So I put this basically predictions next to my table. I appended to my table. So this is number of period, number of characters. These are the value I had earlier. Now I predict this value for my number of characters, considering number of periods that I have. So if I scatter plot this, we get this. Is there any questions? So this is again the same regression line using this equation that I just showed you. So what I'm showing here, different ways to get this line, get the regression line. You see the first time, I just go back to review quickly. What we did here in this Galton experiment, the meet parents with the child, we did the average. I get this period, I average, then I move this all the way through my data, I get all those average, and I get this line. Then I see this is exactly same if I draw the line using my R value. So you can see it's following exactly the same thing. So it means if I predict using my R, I get these data, okay? So it looked like the same with getting the average. That was one way. Then here, what we are doing here now is I'm doing the same thing using the slope and intercept concept, calculating the values. Any questions? Okay, so again, I said that is like that equation, that linear equation. Basically, what I'm doing here, if I simplify it, I can say I'm considering this linear equation, a multiple x plus b, and I consider this linear equation. I want to see if this linear equation fit in my data. And I see it fits perfectly. This is the best fit for my data. I can have and maybe another fit value here, but it doesn't fit quite well. As you see, if I line is like this, it doesn't quite fit all the data. So this yellow line that I draw is the best fit for my data, which is I calculated using that linear equations. So no questions so far? If no, let's have like a 10 minutes break. Okay, guys, let's continue. I hope you're back. If you're back, please turn on your camera. So you remember this one that we just showed you? So if you get this slope and intercept for this yellow line for the little woman, you get basically this value, this slope, this intercept. So basically this yellow line here is this equation, right? Your y is equal to your slope, like 87 almost, multiple x, 87x plus 4,745 if you round it. So if this is a linear equations, right? So this the line I'm drawing here, basically the yellow line is this equation. That's all when we are talking about basically the regression line. This is what we are talking about. So basically this equation fits my data, this data that I have. So let's talk about least square. I mean, you saw that when I draw this regression line, some points falling above it, some point falling below it, some of my, for example, this is my prediction line, some points are beyond my predictions, some points are below my predictions. So let's talk about those errors. So this least square is the has basically a very important application in data fitting when we're talking about data fitting. So errors can be basically considered as your actual value minus your estimations. So I have this estimation, as again I said, there are some values that are beyond my estimation, some are lower, so some of them are negative, some positives. And so we can use these errors to measure the rough size of the errors. In order to do that, we get the square of the errors to eliminate the cancellations, because some of them are going to be positive, some of them are going to be negative. So we don't want them to cancel each other. So we get the square of those numbers. Then we take the mean of those squared errors. Then we take the square root to fix the unit. So you can see the process is something like a standard deviation that we did. In order to calculate root mean square error, or RMSE in short, root mean square error. So I'm going to look at those errors that are falling beyond or below my regression line or my predictions. And I'm going to square those errors, get the average of them, then they take the square root of those average to calculate my root mean square error, or RMSE, and see what that can tell us. So again, I have these functions here. I'm not even talking anymore about the codes, just you can look them. What they do is here is looking at my little woman data. Okay, I'm going to scatter the little woman, is going to draw my basically regression line or my predictions, then going to calculate a certain number of errors, as you can see here. So this graph shows, this is my prediction line, the one that you just showed here, using this method, the slope and intercept. So this is my regression line. These are the errors that I can see. There are some of them are positive, some of them are negative below this. So this is my slope and intercept. Okay, so see these errors. Okay, this is the line, this is the errors again. So I can draw different, basically different lines with different intercept. Okay, intercept and slope. So what this function does basically getting the slope and intercept and drawing this line, then calculating the errors. That's what it does, the slope and intercept. So I can call the same function with different slope and intercept. So in this one, I say, okay, what if my slope is 50, my intercept is 10,000? This would be my line. you can see the errors are much bigger. Of course, there are some errors that is smaller. For example, here, these few lines are now, there's much smaller errors. You can see some part here, like this one, this particular one, but others are showing way more bigger errors. So what if my slope is -100 and my intercept is 50,000? I get this line with these errors. So let's calculate that errors, that RMSE, and see what that data tell us. So I defined a function to get that slope, intercept, and basically print this root mean square error, or RMSE for me. So I do the same for that this line that I did here, 50 and 10,000. So this is the one. So I do this. I get basically for the slope of 50, intercept of 10,000. My root mean square error is 4,322. So let's see if we can minimize that. So for my -150,000, the root mean error is way higher than this. It's 16,000. Let's call it with another slope and intercept. So what if my slope is 90, my intercept is 4,000? I get this line. So now it's much closer, the error, the root mean square error is much smaller, right? It's get 2,700. So what if I call it with my original slope and original intercept? Am I going to get higher than this, lower than this? Or the question is, what would be the line that gives me the least error, least root mean square error?
It would be the regression line, wouldn't it?
It would be exactly, it would be the regression line. If I, this is my regression line with the slope, the original slope, regression slope, and my regression intercept. So I'm calling the same function with that. This is the line. It's pretty close to this, but it's still better. I get 2,715. Here I'm getting 2,701. So it turns out that your regression line at the end will give you the lowest root mean square error. So now this is another way to look at the regression line. So you see, we so far we talked about different ways that you can look at this regression line. This is another way. If your regression line can be basically the line that passed through all your points and gives you the lowest root mean square error. That's another way to look at this regression line. So let's go. So you see, this least square line is minimize the root mean square errors among all the lines. It's equivalently minimizing the mean square error. So this is root mean square error. This mean square error doesn't matter. You can get root or you cannot get. You don't want to get the root. It is still the same concept would be applying for both. Let me see if I'm recording. So this line has different, this basically least square line has different names. You may hear it from best fit line, least square line, regression line. So those are all different definition or name for the same thing that we do. Best fit, least square line, regression line, those are all the same things. Okay. And in the code, I show you that's how it's exactly the same thing. Here, I'm not doing the regression. Basically, I'm minimizing these functions. And I see with my regression line, it gives me the minimum value in my root mean square error. So that can be my regression line. I can look at my regression line as any line that gives me the lowest error. That can be another way to look at regression line. So that basically least the square line can be useful in different concepts too. So let's talk about numerical optimization. It's basically what we want to do with numerical optimization is you want to have numerical minimization is you want to, for example, in that particular function that I show you, you want to find the number that minimizes your error, right? Or optimize your error. So lots of machine learning uses that numerical minimizations. So in the function like mean square error, it returns the mean square error of estimation using the line, right? Using this estimate of my regression line, a slope and intercept. So it turned out that we have these functions in Python. The name is minimize. If you call any function or any function using this minimize, it returns an array where this array is basically A0 is the slope and B is the intercept of the line, which minimize the mean square error among all the lines, all the possible lines. So if you call these functions, minimize certain functions, you get basically your intercept and slope, your slope and intercept. So let me show you in which I believe would be much more clear. So this is my that little woman mean square error. So here I'm calling it with this slope and this intercept. I just come up with two different intercepts. So remember, this is now mean square error. I'm not getting the root of this number. If I get the root of this number, I get the same value. Okay, so don't get confused. It's the same thing. We just may have different name for it. So I just here I turn out I don't want to get the final square root of the value. I just want to have it like this without the square root. So look at this. If I define the function like this, okay, I define the function, my y is equal to x minus 3 to the power of 2 plus 1. This is my function. And if I call this with different values, I get, like, for example, for f1, I get 5, 2, 1, as you can see here. So this is, as this is exponential function, you expect it to reach a certain minimum, right? It comes reach a certain minimum, then it goes up. It never comes back again. So you have a certain minimum here. So if I call it with that minimize function that I show you, this is my minimize function. This is the internal Python comments, and this is my f, the function that I defined here. If I call it this one, I'm going to get the value that gives me the lowest number. So the value is like 3. You remember Python showing like this. This is basically the 3. It just shows sometimes like this. So basically what it means, if I call my functions here f by this value 3, I'm going to get the lowest value. As you can see, f3 gives me the lowest value. So now I want to use the same thing with these functions. If I call it, I get this value for my slope and intercept. So basically what it does, it goes through all the possible combination between the slope and intercept, and it gives you the value that gives you the lowest mean square error. And so this would be this. And if you remember, this is exactly like my regression line, slope and intercept. This is the slope and this is the intercept. For my regression line, this is the slope and intercept that I receive by minimizing my mean square error. Are you confused enough? Yes?
I have a little question.
Okay.
Would it be better to use what we computed or to let the minimize function return the value? because I'm seeing a slightly different results in the decimal points. I don't know if that would be significant.
It is the same, exactly same. I mean, the point
Yeah,
here is
exactly.
like Python is basically rounding up the value at some point. Even for example, here, the actual value is 3. If I call my function with 3, I'm going to get the lowest one. But just Python, this is I think we'll talk about this in a second week. Python turns out to show like value, something like this. It's basically 3, it just rounded up. Or here it's rounding up in a different way, but with pretty good estimate up to here, they are the same.
Okay, so it would be the same. It's not significant, those decimals.
It would be exactly the same. So the
Okay.
point is, either you want to go through all this pain, define the functions, calculate your, I don't know, the line, intercept, your slope, or you just want to call these functions to do everything for you. So I went through all this pain, or I put you through all this pain to let you basically tell you three things, to tell you you can look at that regression line in different ways. It has different names, as I mentioned here. So you can look at it also in a different way. So remember in one example, we get the average, we draw all those average, and we try to predict using those average. That gives us my regression line, pretty close to my regression line. Then I did my regression line using that equations. Then I show you that even if you get the least square line, it gives you your regression line. You can look at it like a line that minimizing all the errors. So that's why it has different names: best fit, least square line, regression line. They are all basically result in the same thing. Or if you have these functions, you can just call it with this minimize to get your slope and intercept, which is again the same things. So let's look at the last one, the last table. I'm finishing. This is a shot put table. Anyone knows what is shot put? Anyone is interesting in Olympic Games, like weird Olympic Games? The shot put is the one that they have this ball, the like iron ball, like very heavy. They hold it like they turn and then they throw. That is the shot put sport. It's part of the Olympic. So this table shows the shot put distance that the different athletes could throw the ball. Okay, with the, I think this weightlifting is the one that they were practicing with. So they were practiced with certain weight. This is a certain distance that they could throw that heavy balls. So these are the things I want to visualize before quantify. So I scatter plot. So you have these functions here, okay? If you put this fit line, it just draw your regression line. So sorry to put you through all this pain to draw the regression line. You can draw it like this too. Just in your scatter plot, put the fit line equal to true. It draws your regression line. But what you can see here, this is my linear regression. Okay, I'm looking at it I'm drawing it basically a linear equation here. But look at this particular dot here, this particular outlier, which is different. You may look at this and you may say, okay, if I remove this fit line, you may look at this and say it's not exactly the linear, maybe it's like a little bit curving, okay? So that's why, what if we try to fit to these different equations, not a linear one, but a like exponential one? Maybe this is going to give me better estimation. So what I'm gonna do now, I'm gonna take these equations and I'm gonna fit the line to this data to see if it's giving me better estimate or not. So I define the functions to do that. So I call this function, you remember minimize? So now my minima is going to minimize these functions for me. So what this function is doing is getting this A, B, and C in my equations and trying to minimize this. So I get these values for A, for B, and for C in these equations. So if I now scatter that with this line, I'm going to get these values, which is pretty much, what I see is better than my linear regression line. This line, the yellow one, is getting much closer to the prediction comparing to this one, right? So turn out that least square error can also be useful, not just for linear relationship, but for different type of relationship. About this. So regression line let us make predictions. That's what we saw. We find R with X and Y in a standard unit, or find the slope and intercept that minimize your mean square error. That was two different ways to get that regression line. But also you can use that for minimizing nonlinear functions. That mean square error, you can use it for minimizing nonlinear function as well. So basically that nonlinear function is your nonlinear regressions. So far whatever we talked about was linear regression, but you can see that minimizing your nonlinear function, the one that I show you in the shortcut table, it's basically your nonlinear regression, this one. So any questions so far?
How would we, I don't know, assume or know that the best curve would be a quadratic or of any other order instead of a linear one?
Okay, pretty good question. It's like you say, okay, I see the data, I want to draw this, and I think that's pretty good estimate for my things. But what you can do, you can, I guess, you can experiment with that list, basically, let's say mean square error. Okay, you can compare this with this. I let that be like a activity for you. You can calculate this errors that this line gives you, the error that this line gives you, and see which one is better. I mean, just by looking at it, as I mentioned, you can. That's why I'm saying it over and over, like visualize then quantify. But if you visualize this, you may say it's a linear with some outliers, but if you pay closer attention, you can say it's not exactly linear. It can be presented with nonlinear equations. Something like, I'm not saying this is the best fitted equation for this. I'm not claiming that. But I'm saying this is the equation that I just come up with, and I want to see if it's representing this. And when I draw, I'm pretty sure this is going to give me less error than this. This line going to give me less error than this.
Okay.
So that's one way you can do that. By looking at it, by trying maybe some linear equation, nonlinear equation, using linear regression. Now you know nonlinear regression and see which one giving you least error.
Okay.
Any questions? No problem. So if there is no further questions, we're done with my part. Now we have, what is this? Oh no, now we have a lab 08 is available in the share folder. Sorry, lab 08. So sorry. What I want to do, I want to divide you to small groups again, group of 3. in order to do the lab 08. It's available in the shared drive. It's available in the server that we have. Either way, you're doing working. If you're working local machine, access it through this shared Google Drive. If you're using the server, access it inside the server. There, it's available. I expect you to work together like maybe around 30 minutes. Okay. And please don't forget to submit at least today. Okay. Do the first submission today. But the deadline, again, like usual activities, is the deadline. Where is my Occupy? The deadline is this Friday midnight for lab 08. The deadline is Friday midnight. But do the first submission today. But if you're done if you finish, you can leave your breakout room, or if it's 12, you can leave, or if you decided to work together, it's pretty fine for me. Anyway, I'm here if you have any questions. So